hear me. Okay, thank you. So today, first some announcement. We asked you about the exam. It wasn't unanimous, like nowhere near unanimous, so we will keep it as is. Maybe for exam 3, we can move it by a day. Okay. Do you want to discuss anything? Any question about the exam? Good. And then right-hand rule. So apologize for my, well, I took that picture from the internet, so I shouldn't even take the credit. Right-hand rule, your hands shouldn't do like this. This is not right-hand rule. Okay. But it should be perpendicular. So basically the idea is force is perpendicular to both velocity or currents and the magnetic field vector. So this is not, I know your paper is 2D sheet, but your screen is 2D object, but this is not right-hand rule. Yeah. 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 Many people don't want that because I think it's a good idea for you to come back fresh. So the idea of spring break is not to exhaust you with studying. And for exam 3, we can move it by a lecture. Any other question? And many of you will be physicians. Many of you will juggle many things and sleep deprived, at least during residency and fellowship. So it's good idea from time to time to stretch yourself. If you make it to, let's say, residency, you will do that. Okay. So when my wife was doing residency, she didn't go home every 4 days, because she had to be at UCLA for on call. Okay. Yeah. It depends on the results. The idea is we want to help you. I'm not going to continue until you guys are ready. Okay. So the idea is we will help you, so you don't need curve. And the idea, the bad thing about curve is basically you compete against each other, which I prefer not to enforce. I'm happy if all of you get A+ in this class. Yeah. Oh, and I need to get back to you. As of this morning, I think it was due, or last night, 6 days from last night, I think. But I'll check. Okay. Any other question? And then there is open door. If you have little brothers or sisters, good time. So this Saturday, 1 until 5. And then at 6, there is a big event on campus. You guys know that? It involves number 20 team in the country, which is Washington State University, against SU at 6 p.m. I'll be there supporting both teams. Okay. All right. So let's recap. So the outline today is, well, I can just show you the outline. The outline today is we will first do recap of force on a wire, and then we will go through magnetic dipole DC motor, which is very useful, torque, and solenoid, wire, and loop. So if we have a current and it flows, let's say, to the right, the force per unit length, or the force for a wire of like L in presence of the magnetic fields, is equal to I times the length of the wire, L is the length, times the strength of the magnetic field. And the direction, I'll just a unit vector, which is basically 1. This one follows right-hand rule. So right-hand rule, okay? So I put this iClicker question. I think most of you answer A. Let's see if that thing is the correct answer. The force point to, let's see. Let me stare this screen with you. So the force, which is your thumb, points to the right. And then magnetic field is your middle finger, points towards the screen or your computer screen. That means the current should go down. So that means the current has to go from top to the right and then down to the left and down again. So the correct orientation of the battery is A. Okay. So I think all of you basically ready for exam 2. Next, we can skip some of this since we have a lot of questions. So next, I want to discuss basically a standard way of discussing this topic. Basically, we will talk about DC motor. DC motor is very useful. If you are fortunate, you drive Tesla. If you like it, good for you. Some of you are fortunate to have electric skateboard. If you are old, you should hang out. If you're not that old, I'm not going to hang out with you because it will be creepy. But electric skateboard basically use DC motor. Okay. But first, this one actually a good topic to discuss magnetic dipole. And you may think that magnetic dipole is the analog or magnetic analog of electric dipole. Basically, electric dipole is you have two equal charges, +1 and -1. And if you have electric fields, this dipole will align itself. Well, the electric field should be point this way. Will align itself. Okay. So for electric dipole, what you will see is that it basically involves a loop. It can be a loop as big as a DC motor of a big machine, or like this rectangular metal here, or can be as small as a single atom. Okay. And if you expose a magnetic dipole to a field, it tends to align the dipole to the field. This is a closed loop. Okay. So some of you may think that this is not aligned. Well, in math and in physics, we came up with a way to describe an area which involves a line that is perpendicular from the plane of the loop, which we call a normal vector. So the normal vector will align to the magnetic field. So you need to pay attention to this lecture because it's really tedious. As you can see, there are so many red arrows, so many loops. And if you don't get it, you should spend time on it. But it's fairly complex. So basically, let's say we have this loop here, and I'm gonna try to match the direction. So the field goes, okay, so it's kind of difficult. My drawing will be slightly different than your textbook. I like the magnetic field to be horizontal instead of perpendicular. So we have a magnetic field, B, okay? And then let's somehow apologize for my artistic scale. It's not perfect. So, and then you could, let's say you place a loop in right here, okay? And this is good. So we can do, let's just do clockwise. So the current goes up, right, down, and left. And then this motor, right now there is no axis, but you can imagine that if this one works, if our idea works, I don't know who came up with this idea, then it will rotate along this axis. Okay. Sorry, it should rotate along different axes. Along this axis. Okay, so let's see, now we can, our next job is to figure out the direction of the force. Sorry, this I, the current is in red. So I. So if I is point this way and magnetic field goes this way, then the force points like this. Let me use different color. The force point to the center. So I, and then the magnetic fields point left from right to left, my right to my left, and then I goes to this axis here, so it goes inside. This one is also, so I goes up, magnetic field I goes up, magnetic field goes, so all of this goes to the center of the motor. Anyway, so basically using a right-hand rule, you can calculate, or you can decide, or you can determine the direction of the forces along this side and along other sides. Any question? Okay. So basically, using the same right-hand rules, if you look at side view, this is side view, then what I'm drawing here is like that. But you can imagine if there is an angle, then there is the angle. So right now the forces are either for this part of the motor is up, for this part of the motor, which is this side, goes down, and and from this side it goes into the plate and out of the plate. But if there is angle, so this loop here, so right now the loop looks like this, but I can make the loop, and then let's say the loop can rotate. When the loop rotates, then this there is this force here will point up, and this force here will point down. Okay, I don't know how to draw this better. Sorry. So what I'm trying to show you here is that this side of the loop will be pulled. Sorry, how to draw this? So when I draw this, you know that there are two sides of this line here. Is that, do you get that or no? So one side of it will be pulled up, the other side of it will be pulled down. So let's say, so it's like this, okay? Let's say the current points up, so currents and magnetic field points that way, then there is well, in this case, the current have to point the other direction in order the force to point up. So when I say it's tedious, it's actually very tedious. So it has and then basically, if the orientation is not, if the plane is not parallel from the field, when I say parallel is the normal vector of the plane, then there is a net force and there is a torque. Okay? When I say net force, it's actually net torque. Sorry. Let's okay. So basically, if the loop is parallel from the field, then that's the state with minimum energy. But if it's rotated, there is a torque. Okay. And then let's just derive the formula. The force here, it's actually perpendicular because B. Okay. Let's say B is from left to right, and I is the direction of the current, either goes up or towards you or down or away from you. The force is given by I L times B. Right. There is a sine theta, which we will add later. And then the length of the segment, your book use B for the shorter side and A for the longer side. You see my cursor? So A is for the length and B is for the width. Okay. So torque is given by F times R, and there is because the direction of the force and the radius here and the distance here depends on sine phi. We put sine phi here. Okay. And this one is equal to, so tau is torque. I hope you still remember what torque is. So torque is if you have an object, let's say this is the motor and it rotates like this. If there is a force of a distance r from the axis of rotation, then torque is the force times the distance from the position of the force to the axis of rotation. So this r here is b divided by 2. So this motor or this dipole rotates clockwise. So r here is b divided by 2. And F here is equal to I L B, and L is equal to A, because A is the length of the segment that has this force here, that experience force F. Okay. So I A times B. Okay. So torque is equal to I A B times small b. So b is the width times sine phi. So this is the torque due to the force. So the force that I'm highlighting right now. But there are 4 forces. So this segment here, there is a force. There is a line with the axis of rotation. So there is no torque. The third force here it has non-zero phi, so there is another torque, and the last contribution, the last force contribute to zero torque to the loop. Okay. So if you use symmetry, basically the third one is the same as the first one, so I'm just gonna multiply by a factor of 2. And then the second and the fourth, they have zero, they contribute to zero torque. Sorry, this one b divided by 2. And then 2 cancels. We end up with I times A times B. Times B times sine theta. A times B, which is the area of the loop. So this one also is equal to the current times the area. And I'm gonna put a bracket times B times sine phi. And this is, we define A times I to be magnetic moment, or in some textbook, they use the symbol mu. So this one, the torque is equal to M times B times sine theta. So basically, in terms of like conceptual understanding, this is like what I said before, which is if you have a loop, and it has currents, that thing can be either a DC motor that you drive with power supply with a battery, or it can be an electron that circle around a nucleus. Then if you apply magnetic fields, it will align to the magnetic fields. So this is why we call it a magnetic dipole. Okay. Any question? Good. So it's a complex system because there are 4 forces. You have to do right-hand rules multiple times, and your book make it worse by using phi for both the angle in right-hand rule and also the angle of the motor. And there is capital B, there is a small b, capital A, small a. Just be careful when you read Prozol. So I have this iClicker question. Remember the concept of magnetic dipole. Okay. Under a magnetic field, it will align itself. It will align its normal vector to the external magnetic field. Okay. So the question is, a rectangular loop is placed in a uniform magnetic field with the plane of the loop perpendicular to the direction of the field. If the current is made to flow through the loop in the sense shown by the arrows, the field exerts on the loop is, okay, so I give you a minute. You can discuss it with your classmate. Twenty more seconds. Three seconds, 2, 1. Okay. So do you want to see the results? It's basically uniform distribution. So that means I didn't deliver the material well. Okay. So we can either use our understanding of magnetic dipole, which is in the presence of external. So basically a loop with a current is a magnetic dipole, either a single atom or a gigantic DC motor. DC stands for direct current. Okay. So because the loop is already aligned to the field, when I say align is its normal vector is aligned to the field, then it's already happy, meaning there is no force. That's the position of the lowest energy. It will not move. If things don't move, because it's already aligned, that means the net force and net torque is equal to 0. So that's a fast way to answer that question. A longer way is you use right-hand rule. So the field goes up, so current goes to the right, field goes up, then you get field like this. Similarly, for the other side, it's the opposite, so it cancels. And then for this one, the field goes up, and the current goes towards the whiteboard. So the force, like, excuse me, do you have question about this? Okay. If you need to do, like, to have a big discussion, you can discuss it outside. I will not take it personally. Okay. So the sum of the force is 0. The torque, these two sides don't contribute to the torque. These two contribute to the torque, but they cancel. So the sum of the torque is also 0. So the correct answer is D. Because of time, it's already 10:40. The second question is different, and it's actually tilted by 90 degrees. And with physics, you can answer this fast. But I will leave this as your homework, and I will tell you the answer. The lecture notes that I will post later today will have the answer. So if it's a little bit more difficult, it's by design, because I want to prepare you for the exam. Because I don't want you to feel that I trick you. The iClicker question is easy, and then the exam is hard. So right now, towards that exam, the iClicker question will be more and more difficult. And by the time of the exam, everything will be so easy for you. So this one is another way of asking the same question. This is about the idea of magnetic dipole. And just be careful when you read this question, and I will do my best to provide you with a drawing, because I can either ask you about the normal vector or about the plane. So the plane of the magnetic dipole at the lowest energy is perpendicular from the external magnetic field, but the normal vector is parallel with respect to the external magnetic field. So it depends. Here is the angle between the plane of the loop, so it's 90 degrees. Sorry, what's going on here? I think I remember this. This morning I changed my mind, because I always talk in the context of normal vector. So this one should be 90 degrees. But on the exam, I may ask you either angle between the plane of the loop or the normal vector. Okay. Apologize for that. Yeah. The plane of the loop is like this. So let's use the DC motor. The field goes from DC motor configuration. The field goes from left to right. Then this is the lowest energy with 0 torque and 0 force. So the plane, I consider this as the plane, right? And the field is from, 90 degrees, which is C. Yeah. Okay, sorry. It's the maximum torque. Sorry, the question is maximum torque. So the answer is, you're correct. Is A. Sorry, this is I juggled the lecture notes at the last minute. Okay. Yes, please. Yeah, it's basically zero torque. Yeah. So, if you are interested, the energy as a function of angle looks like this, and 0 is, so U is the energy of the magnetic dipole. And this one is basically mu B sine theta. And you can, this is also for your homework. It's basically units. One thing to test our derivation, whether it's correct or not, is by checking the units, and I'm pretty sure you can do that. And there is a typo here. It should be B only, and I will fix it. Initially, the problem has more than one correct choice, and then I decided not to do that. So I deleted option C. The previous option D is option C right now, which is not right. Okay, so so basically we have discussed this the concept of magnetic dipole, if it's complex, because it is, but I'm pretty sure with if you read it one more time, you can understand it. So there is a nice demo online. So this is a demo. This is from Korea. It's a Korean website. I don't know why I mentioned from Korea. So this is basically a DC motor. Red, I think, is, sorry, red is North Pole, blue is South Pole. That's the magnetic field. And the current, okay, so basically we have this loop, okay? And then let's say there's magnetic field from your left to your right, and then it will stable when the loop is in this configuration. You read this on Pruso, so it can rotate and then stable like this. So how to solve this problem? So if you want to make something useful out of it, like Elon Musk tried to make something useful out of current carrying loop and magnet, how would you solve this problem? Because this is not a motor. If you have, electric skateboard, this one will take you, I don't know, 1 foot, and you stop. How to do that? Somebody who's sitting in, yeah. So one, basically you turn on and off. Okay, any other suggestion? I have something. Let's see if this works. It's too small. Okay, so any other suggestion? Who's the lucky one? Shreya, is she in the class? Shreya is probably doing something else. Let's hide the roulette. So one thing is we can use AC instead of DC. AC is alternating current. That might work. If you are fast and you have nothing better to do, what you can do is you can change these two poles, positive and negative, if you have really fast hand. But that thing is not useful. It's like high maintenance. motor. So, so this is the difference between, or this is where engineer, I consider myself as first scientist and then second engineer. This is where an engineer or applied scientist make a big difference. So what they do is they have the name of the component is commutator, which can commute the position of the electrodes. This commutator is pushed by spring. So these two are springs. So it always touch these two metal. So what happened is when I run this, so initially part of the loop that hits the negative electrode, after half rotation, it swapped to the other electrode. Did you see that? I found this thing very impressive when I was your age. And then this simulation is, the QR code is on your textbook, and it has all the forces that that should help you learning DC motor. So next is a loop. Okay, we are transitioning to the second part of magnetism. The first part of magnetism is about how physical system feel and experience forces. The next part of the magnetic field is how we can generate a magnetic field. This is no different than electric field, than the charges. Charges, a single charge can produce field, but also react to external field. Right? The first loop that, the first system that I will introduce is a loop, basically a circle. A circle, if we flow currents, there will be flow, there will be a field that looks like that, but because getting the field involve messy integrals, then what I will ask you to do is just to calculate the strength of the fields at the center of the loop. And this is a circular loop, okay? And not only that, I will ask you to tell me the direction of the loop. Because if you have a loop and you know the strength, the direction can either point up or point down. And not surprisingly, like anything else in this class, we use right-hand rule. So if the loop looks like this, imagine this is a circle. If the loop, let's say, if the currents, if you flow current and current goes counterclockwise, in front of me it's counterclockwise, then the direction of the magnetic field at the center follows right-hand rule, which is I curl my right hand, and then the direction of my thumb is the direction of magnetic field. Okay. Any question? So in the past, I forgot to bring a knife today. So I think I say to my students that it's like if you wake up early in the morning or on the weekends and the clock rotates clockwise, then the direction of the field is the direction when you step that clock. Sorry, I forgot to bring a knife today. And we can, do you want to do iClicker? Yes, okay. Good. So iClicker is on. So the formula, let me write it down. So the fields at the center of a loop, at the center of the loop is mu naught times I divided by 2 divided by the radius of the loop, okay? And mu is called permeability. This is just a number that characterizes how a material, such as vacuum, respond to magnetic field. and that number is basically 4 pi times 10 to the minus 7. So 1.2, sometimes it's easier to think of that as 4 pi. So this is the equation. So this iClicker question should be fairly straightforward for you. So the question is, consider two current carrying circular loops. Both are made from one strand of a wire and carry the same current, which is I. But one has twice the radius of the other. If the magnetic field strength at the center of the smaller loop is B, smaller loop, what is the magnetic field strength at the center of the larger loop? Let's spend 30 to 60 seconds on this question. Okay. All right, 15 more seconds. So half of you get it right, but you cannot see the iClicker window. Okay, so 3 seconds, 1, 0, good. So what is the answer? The answer is D. So basically, B small is equal to B is equal to mu naught I divided by 2R. If we double, so B large is equal to mu naught I times 2 times 2R, which is equal to 1/2 mu naught I times 2R. I don't know whether I'm making it easier or more difficult to use. I added small to make it easier, but your book says B small is equal to B. So the answer is 1/2 B. Okay. Any question? Next is what we call solenoid. Solenoid is basically a series of, it's not a series, it's like a spring. So it's like a helical circles, no, a helical cable. You roll cable in a helical fashion like this. This is a solenoid. And this is actually how I made solenoid when a stockroom was closed. And I really want to run my experiments. I just made solenoid from scratch. You can model solenoid instead of as a helix, instead of introducing you the equation of a helix, as a series of circles, and each circle has a field strength. The center of each circle has the field strength of mu naught divided by 2R. But there is an easier way to calculate the fields, which is using Ampere's law. Since we only have 5 more minutes, we will discuss Ampere law on Friday. And maybe we can discuss this, we can do this experiment. We can do this iClicker problem on Friday. Okay. So next is, if we know the fields of a circular loop, which can points up. So when I say points up, it actually looks more like this. It points up at the center, but if you are under the center or the axis of the loop, the field goes into the loop. So it's actually, so when you, let's say when you superimpose or when you put a lot of circles or loops, the field will look similar to the bar magnet. So this is one way to view bar magnet, which is basically a series of loop. And if you think about it, it's how magnets are made of. So inside magnets, there are many atoms, and each atoms there is an electron. An electron, let's say for this material, let's simplify our life, it only has one electron, so the movement doesn't cancel each other. So what you have is a material with many electrons, and each electron are loops. And because of that, a magnet can generate magnetic field. Now I have a question for you. So if you zoom this region, so I'm going to zoom this region. They cancel each other, right? The current due to the movement of the electron cancel each other. The bottom left point to the left, the top right point to the right. So how a magnet can generate magnetic fields? If many of them cancel, the hint is on the right. Yeah, so the outside part of a cylindrical magnet, they don't cancel because there is only one loop. So in the end, if you sum all of those small currents, you get one rotating current. So one way, if somebody asks you, I heard that you're taking, somebody gossiping about me, I heard you're taking result class, and they ask you, why isn't everything magnetic? Why can't, what do I choose? Potato is magnetic. Then the answer is because, you guys know the answer to this question? It actually doesn't really relate to the previous slide. Turns out that many materials, they have more than one electron. So those movements, they can cancel each other. So that's the reason why most materials are not magnetic, because the orbits of those electrons cancel each other. Okay, so next we will do a magnetic field due to a wire. Any questions? If not, I'll see you on Friday.